Hello and welcome back. In this video, we're going to talk about data structures and algorithms first topic, or the introduction topic, that is introduction to algorithm. Okay, in this topic we will be discussing, or in this video we'll be discussing what is algorithm, what kind of problems. I'll be discussing few examples where we have applied algorithms or we are going to apply algorithms, and then what exactly algorithm is as technology, what if we don't have that constraints which we have now. Okay, let's move forward without further ado. So what exactly algorithm is? Algorithm is nothing but a well-defined, well-defined conceptual procedure which takes some values or set of values that is called as input and give some values or some set of values as output. Okay, so an algorithm is a sequence of it is a sequence of conceptual steps that transfers the input into the output. Okay, we put some input and we get some output. Like we use algorithm almost in daily life. Yes, like making a tea, baking a cake. Yes, taking water from jar, everything requires algorithm, right? Or everything is an algorithm almost. To take some technical example, like if we want to sort a series of numbers, let us say we have few numbers like 31, 41, right? 5, 3, 51, 91, like these, and we need to this is our input. Now there will be some conceptual steps over here which we will be seeing. We have many sorting algorithms, to name a few. We have quick sort, yes. We have heap sort, count sort, insertion sort, merge sort, bubble sort, many different algorithms, yes. And our output will be something like 5. If I want to have an output of non-decreasing order, it is increasing order. So sorry, not 5, 3, 5, like 31, 41, 51 and 91. These will be the output basically, right? So this is algorithm. We are going to have some steps over here which is going to do this thing, right? And you're going to get a desired output. Yes, so this is algorithm exactly. Now let us see, where do we apply these algorithms? Yes, means we apply these algorithms in many places, but here are some few examples which I have considered. This one, basically the human genome project, is a very quite is a very nice example for application where we have used algorithm. And this algorithm, the goal of this particular project was to identify all the 100,000 genes in the human DNA and determining sequence of 3 billion chemical base pairs that makes up our DNA. And where do we have used this algorithm? Where do we have used the algorithm is like storing the data, analyzing the data, and developing a tool to analyze this data. So we have used algorithms in biotechnology also, that is human genome project. The next is an example, the next example that, or next problem I'll consider is an internet. Okay, people got connected due to, since internet has came into existence, and you can like you can quickly access and retrieve large amount of information through internet, right? So with all the clever this is just due to clever algorithms that sites on internet are able to manage and manipulate these large volume of data. For example, if you want to search for something, okay, if you want to search for something, like if you want to search for the word algorithm, right? So this algorithm word is going to get searched in the whole internet. I mean, like uh, getting the shortest path so that you can reach that particular word algorithm. So this internet also uses multiple concepts of algorithms or data structures, like hash tables. Hash table, you will study this, and this hash table is used to like store this, to get the position where this particular word algorithm is stored. Then we use shortest path algorithm, right? Shortest path algorithm. So to reach, the internet is connection between multiple ports, right, multiple points. To reach that particular point, you can have multiple ways, right? So to reach this particular point, you can have multiple places, and which is the shortest path at minimum time. We need to reach that particular word algorithm, so we're going to use shortest path algorithm, which is also a concept of internet. Then we also have string matching, right? So these are all the topic which are useful when you study internet. Okay, and all these topics we're going to study. The third example, or the real life problem which I would like to tell, is like manufacturing and other company, commercial enterprises, they also uses algorithms. How so? you know if this particular manufacturing companies or commercial enterprises have their funds, they need to utilize these particular things very carefully. So when these enterprises need to allocate, they often need to allocate these resources, this scarce resources, in the most beneficial way. Let us consider there is an airline company. Okay, the airline company may wish to assign crews to flight in most efficient way by following all the government regulations, right? There might be some internet service provider company. Okay, that provider may wish to determine which place they can have additional resources so that the customers are happy or something like that. So manufacturing companies and commercial enterprises are using algorithm for solving their problems. Okay, now these were all three real life applications, I can say. The another two are, these are this is beyond the scope of the course or the series which I am taking, but the concepts you will be understanding. But these two are the problem that we will be solving. Okay, the first is shortest distance in the roadmap. Let us consider, like we have 5 to 6 cities. Okay, like A, B, C, D, E, F. You need to start from here and you need to end here. Okay, this is your ending point, your destination and your start. Now you need to travel, and there are multiple routes to reach F. Okay, there are multiple routes to reach F, right? And you need to find the shortest route. What route can I take so that I can reach reach my destination in minimum cost as well as in minimum time, right? So here we use shortest path algorithm. You will be given the weights of all the distance, or the distance between all the cities. Okay, and you need to find the shortest path, shortest distance in the roadmap. Okay, which will help to reach your destination. So this is one of the most famous example, and here the concept graph is used. And to name a few algorithms for this, we have Dijkstra's algorithm, Bellman-Ford algorithm. Okay, so here it is like shortest path roadmap. Okay, another thing, another example you can see over here, that is the longest common subsequence. Okay, longest common subsequence. Let's take some again real life example. Now let us consider you have two DNA strands. Okay, you have two DNA strands as A, T, T, C, C, G, A, T, A. Okay, this is one DNA strand, and the other one is something like let's say C, G, A, T, C, C, G, A, T, T, or G, A, T, A. Okay. Now in this what you can see is we have two DNA strands. We need to tell that these two are related to each other. We need to compare them. Okay, so how do we compare them, or how can we say that these two strings or strands of DNA are same? You can say this by comparing the longest string that is in both the longest element, continuous element subsequence, which is in both the strings. Like over here in our example, we have I guess A, T, T, C, G, A, ATTCCGA and TAA. Okay, so this is the longest subsequence that we can get, and we can say that the whole strand, if I'm not wrong, I guess, no, I'm wrong. Okay, I guess you understand what I mean. Okay, so something like this and something over here, these two are same, I guess. And here what I have written, I guess, T. Okay, so something like this. Do you understand? Means this is the longest subsequence which is present over here, and this is also present over here, and we are going to see this, the most efficient way, by which we can, get the longest subsequence. We are going to have some algorithms for this too. Okay, to name a few algorithms, I guess we have Prime's algorithm and some dynamic approaches also. Okay, no, we have dynamic programming, so this topic comes under dynamic programming, so we're going to see that also. Okay, to name more few if you want, there is a concept called convex hull. Okay, convex hull, you can understand this, you can find out in Wikipedia, you can get everything about it. Then the seventh problem, or one more problem if you want, you can you can search for topological sorting. Topological sorting, you can get n number of applications from topological sorting. Okay, one of the most famous problem and has many applications. Yes, so this is about what kind of problems are solved by algorithms. Another thing that I want to talk to you about is NP complete problems. There are some kind of, sometimes you get through problems which are which you have just single solution. You cannot have every time when you will be studying algorithm in in future, or whatever algorithm you will be studying, you will be finding the most efficient, is it the most efficient algorithm, right? So the time will come sometimes that you will not be confirmed whether this is the efficient solution or not, and you will be doing some fruitful or fruitless search for finding the efficient algorithm for that. But there are some problem for which only one solution exists, or there is no efficient solution for that. You should know that this is the problem which is NP complete problem. It can have just these solution, it cannot be having any solution which is more efficient than this algorithm. Okay, so there are some problems that is called as NP complete problems, which are having just single solution, and that solution may be effective, may not be effective or efficient, right? So there are three interesting properties of NP complete problem that I would like to discuss. Okay, three interesting properties of NP complete problem. The first is that no one has ever found efficient algorithms for these problem, right? There is just a single solution. Okay, we will discuss a problem, there is just a single solution, and that solution is efficient. We have considered there is no other solution for that problem. Okay, so although no efficient algorithm of NP complete problem has ever been found, or nobody has ever proven that an efficient algorithm can exist for that particular problem. Okay, the second thing that I would like to tell you, the first thing was no efficient algorithm exists. The second thing is that if efficient solution or efficient algorithm exists for one, then it will exist for rest of them also. This is one of the most unique property of NP complete problems. Okay, that if you find the solution, efficient solution for NP complete problem, one NP complete problem, then you will get the efficient solution for rest of the problems also. The third interesting point of NP complete problem is that if scientists are trying to change the algorithm statements and get something new from it, right? But if you try to change the algorithm statement or the problem statement of the NP complete problem, then whole solution changes. Okay, you can get the whole different statement if you try to change the NP complete problem. So scientists, computer scientists are like that if you try to change the problem statement, then a big change in their efficiency can happen. okay, and in the efficiency of the best null algorithm can happen. Okay, so these are NP complete problems. To name a few NP complete problems, I'll be naming two. The first is vertex corner problem. Vertex corner problem. This is one of the NP complete problem. The second thing you must have heard, or you are going to hear it, we're going to solve it. That is traveling salesman problem. Traveling salesman problem, and I'll be discussing just a problem statement of traveling statement problem. Okay, what exactly is traveling salesman problem is, consider we have a depot, we have a company, or we have a delivering company. Okay, this is the depot of the delivering company, and we are having few trucks which are loaded every day at the start of the day or at the end of the day. All the trucks are loaded, and in morning they are sent to different addresses every day. Okay, they are sent to different addresses, different places every day. Okay, so they each day it loads up each delivery truck at the depot, and it send it to the deliver goods to several addresses. Okay, at the end of the day each truck must end up back. Okay, each truck must end up back in the depot so that it is ready for the it is ready loaded in the next day, for the next day. So to reduce the cost, okay, to reduce the overall cost, the company wants to select a order of delivery. Okay, order of delivery stops that yields the lowest overall distance as well as cost for the fuel. So this is an NP complete problem. We have different addresses every day, so we need to have, like, you need to sort the addresses, you need to consider the addresses every day, and you need to consider the distance every day. So this is an NP complete problem which can only a single solution exists for it. And what is that solution we'll be discussing when we'll be having traveling salesman problem in our video, in our series. Okay, so this is what exactly is NP complete problems. Okay, moving forward, so before moving forward, I'd like to ask you a question. We till now everywhere I have discussed, like, efficiency on time. Okay, we need to save time. Is there any other factor? Okay, comment down below right now. If there is any other factor by which we can say that yes, this algorithm is efficient? Okay, comment down below right now. Okay, time is one factor, right? Is there any other factor by which we can say yes, this problem is efficient, this algorithm is efficient by this thing also? Yes, this factor also. So comment down below. So these were problems which are solved by algorithms. There are many more problems which can be solved, right? We will be discussing all in the series. Moving forward with what are good algorithms. Yes, we should know what exactly good algorithms are. How can we say that this algorithm is good? By these 6 features, if I'm not wrong. There's 7 features. Okay, the algorithm should be precise, algorithm should have a uniqueness, right? Every step should have some solution. It should be feasible, that it should be possible. It should be practicable in real life. It should not be like, yes, it can happen. Then the input, you should give some input, must accept any set of input, okay, in its constraint. Then it should have the desired output. It should be finite. It should not be like it is not halting anytime, so it should halt at some point. Yes, and it should have some generality. That means the algorithm must apply a set of defined inputs. Yes, that means if I have made an algorithm for which is working for 0 to 60, that means that algorithm should work for all the values between 0 to 60. That means constraint should be satisfied. Okay, precision must be there. Every step should be outlined. Okay, exact. It should not be confusing. Yes, these are all the characteristics of good algorithm: precision, uniqueness, feasibility, input, and all. Okay, moving forward with where do we use algorithms as technology? Okay, let us consider that computers are infinitely fast. Okay, computers are infinitely fast, and computer memory are also free. Okay, computer memory is free. We have infinitely fast computers. What do you think? Would you have any reason to study algorithms? Would you have any reason? The answer is yes. Okay. If for no other reasons that than that you will still like to demonstrate that your solution method terminates and does not does so with the correct answer, right? If you don't, if your algorithm, yes, you will need algorithm because you need to, you know, satisfy all these properties. Okay, you need to satisfy all these properties, right? So algorithm is necessary. You should your solution must have, you know, a property to take input, a property to give output, right? Should halt at some point. It should be general. It should be unique at every step, right? So algorithm is required anyhow. Okay, so if computers were infinitely fast and any correct method, then any correct method for solving that problem will do, right? You will probably want your implementation to be within the bounds, right, of the good software engineering practice, right? It should be properly documented, it should be properly commented, right? It should be readable, of course, yes. So the algorithm will exist, but it should be right. It should have, you know, some software, you know, engineering practice, good software engineering practice, right? But you will most often use whichever method was the easiest to implement, right? So like if I want to sort a number from, you know, few numbers, I'll directly, you know, or if I want to search for a number, right? If I want to search, like we have number 2, 3, 5, 8 and 9. Okay, these are the numbers, and I want to search for the number, right? Let's say 5. What I'll do, I'll directly do the linear search, right? That is also a solution because we don't have any memory issue, we don't have any time issue. I can directly do linear search and I can find 5 going one by one, you know, going one by one to the array, and yes, I found it. But if we have time constraint, we need to consider all the factors. Of course, algorithms are not fast. Memory, you know, they are fast, but they are not infinitely fast. Memories are not expensive, but they are not free. Memory is not free. Still, computing time is therefore a bound resource, and so is the space in memory, right? So you will require space. You need to have the shortest time for the algorithm. You should use these resources wisely, and algorithms that are efficient in terms of time and space will help you to do this. Okay, so if the algorithm is efficient, it means, you know, efficiency. What is efficiency? Efficiency is nothing but something which is, you know, which is bounded, right? Means all the bounds, lower bound and upper bounds, are, you know, considered. Lowest time, it is having some worst time, it is having some, you know, best time, right? Worst case and best case, that is efficiency, right? You should have 100%, you know, efficiency, or not 100% of course, but you should have some efficiency, right? So yes, this is it, that algorithm is used everywhere. Now algorithm as technology, right? You know, we have used algorithm in different technologies also. To name a few, let's say we have used it in object-oriented systems. Then we have also used it on, you know, like integrated web technologies. So web technologies, yes. And then we have also used for fast networking, whether it is wired or wireless, right? Wired or wireless, that is not considered. So we have used all the we have used everywhere. Let us consider a web-based services, you know, like they determine how to travel from one location to another, right? So we have a web-based technology, a web-based service, where it gives us to which route to take. Let us say which route to take for what is the shortest route to reach that destination. Okay, so we need to have fast hardware and we need to have, you know, proper graphical user interface so that we get maximum users, right? So in wide area networking, if we consider wide area networking, and also possibility of object orientation, right? However, if you would also require algorithms for certain operations such as finding routes, right, that is probably the shortest path algorithm, then rendering maps and interpolating addresses, right? So everywhere we are using algorithm. Okay, yes. So I guess this is it. Thank you for watching. You know, you can subscribe, like, and do share. And if you have any doubt regarding algorithms and further, uh, you can ask in the comment section. So this is it for this video. The next video will be analysis of algorithm. The introduction part, you know, the definitions, all the thing that you have seen in this video will be provided as a document file, which will be in the description. You can check that out for sure. Okay, so thank you.